Hello, and this is class 2 where I've already done separate videos for the examples. I want to go to the material selection part of this. Materials can be kind of daunting. There's tons and tons to choose from. So unless somebody else has specified what material you're going to use, it could be a little overwhelming making this decision. So we want to systematically approach this. And there's a gentleman named Michael Ashby who's made his career out of making a systematic approach. And so it turns out he's got a company named Granta. And I have the link to it right here. But we'll see diagrams that they're called Ashby diagrams. And they help you try to navigate the different properties and then try to systematically approach how to select a material. And there's software for this that's available. But this is sort of like an introduction to material selection. And you can see from chapter 2 in Shigley that this has been brought up right here, that these M.F. Ashby developed these powerful systematic method for material selection. And so here's even alluding to the software that's available from them. So some material properties, there's lots of different material properties that might be important to us. A lot of times we just think about strength, or we might think when it comes to deflection, Young's modulus, that's the like related to the stiffness. We might also think about the density, but the cost, the price is also something very important. We don't want to make it out of titanium if it doesn't need to be made out of titanium. It's expensive. It might be strong and light and stiff, but also expensive. So we have to kind of like come up with some priorities. There's a lot more to this decision. We might make a decision-making matrices kind of thing. But for right now, we're going to stick with just a couple really simple treatment of the thing. Once again, this is a field of study where there's a lot really deep that we could go into. But also thermal properties might be something that we would look into. Electrical conductivity might be something that we would want to consider, depending on the application. So we could break down the family, the kingdom, the family, the class, the subclass, the member, and then like the attributes and so forth. So we could systematically break down what kind of material are we talking about. And in these, like for instance, they all have from these different families right here: metals, ceramics, glasses, polymers, elastomers, hybrids. You could see that they have a variety of like traits, like strong, stiff, tough, conductor, strong, stiff, brittle, insulator, comparing metals to ceramics and so forth. It's kind of interesting to try to think about those types of traits. This is just an example of something that I found from this guy, Roy Meck. You could look this up. He's got a lot of stuff. It's kind of interesting, some mechanical stuff. I have links to this on my useful links and resources. But here's some notes about different applications of various materials that you might want to consider, right? So we might even think about like looking down on the applications process and going to the other side. These are some charts that kind of talk about the history, and I find them to be interesting. Maybe you will too. But we find the evolution, and this is prehistoric times. We had they made things out of wood, right? Or they made stuff out of bone and shell and stone, and maybe they could find some gold, and they were able to pound gold and be able to maybe even be able to smelt it a little bit. And then in 50 BC, this is right around just a little before birth of Christ, we had the natural materials. We might be adding cork to that, right? And some ceramics and glass maybe, where we actually can make some glass. We have pottery and brick and concrete, where they might have had pottery before, but now they're actually able to make something out of a type of concrete. I'm sure it's early concrete. But you can see the metals have increased, right, from 50,000 BC to 50 BC. And then from, like, you skipped forward to 1500 AD, you could see between, here's 50 BC, you could see that there's more metals, like, not many more, like this wrought iron, cast iron is part of that. Not really terribly too much. Then we go to 1900, right? So there's 1500 AD. So, like, Columbus is just set sail, just found the new world. But now we got to, like, the beginning of the previous century, and you can see that we have rubber now, and polymers, and some aluminum, and some steels. That's good. We've added in some zinc, but I think aluminum is really the big progress that we made in there, and some of the polymers and rubber. But now we have, like, 1945, so, like, the end of World War II. You can kind of see we're jumping back and forth here. You can see the different types of, we have some more plastics that are going on. And there's magnesium alloys and aluminum alloys and some titanium in there, right? And then, but now we take a look at present day, right? So we have a lot of foams and other polymers. We have some various other things down here in the polymers and elastomers. We have quite a few more ceramics that we're dealing with, and they can be very high. And this is strength versus density, right? I should have said that right away, but you could read the thing and go back and look at it. That we have these characterized. We want something that's, like, lightweight and strong, and so as we could kind of, like, try to go up into this direction. So that's what these Ashby diagrams, right? Here's his strength and density, and we can see that they have these things called guidelines right here, and you can see that they have this kind of form that doesn't quite make sense. I mean, these are just like slopes where you might take a ruler. I guess the ruler would look better this way right here, right? No, let's see, that way. Yeah, okay, that way. And we would, like, slide up and down through them. Let's see, going this way. My camera's backwards, isn't it? Okay. Anyway, so you could find for these guidelines, you could find, like, stuff that everything that's above it would be, like, acceptable for you. So you could kind of, like, narrow it down. But that's just strength and density. You could also plot out these traits for Young's modulus and density, maybe. And you have different guidelines that we could run across. Or we might have Young's modulus versus strength, right? Okay, so we got density out of the picture. So you can start looking for some of these metals, that have high Young's modulus. So they're stiff, but they're strong, right? Over into the upper right area right there. But maybe we want it to be strong, but also flexible, right? So so we might have, like, a low Young's modulus, but a high strength right there. There's also strength versus relative cost. Now, that's an important one to us, right? So we could kind of, like, take a look at these lines and draw those lines, and then kind of sort of narrow down. And the method about which that we go to try to apply this is to create some kind of performance index. And we'll discuss how that's done by way of example. It's a little bit easier to see from example, and you can kind of see that different things are a function of different parameters. So, like, we might take a beam configuration, and we might say, okay, well, we've decided that the stiffness is specified, and we want to have the minimum mass. So we put together assembled an equation right there, and we see what it's a function of, and then we use one of the lines right here. So we can see that we have rho over e to the square root, right? So Where is that? Okay, so now this is reciprocal right here, right? So e to the square root right here. So here would be the line that you would use to try to say, okay, everything above this is going to be something that's going to be a material, or anything that's on that line right there is like maybe is alternate materials that we might want to use. That's the big idea. There's a YouTube video here. You could click on this. It's kind of funny, but it's not going to take up our time. So here's the basics of this. We have 2 examples, and I will go through them. I don't know if we'll be able to do this in class. It's a kind of ambitious amount of stuff for this class. So let me see here. And I have this all written down. Okay, so here we have the that first example right in there. For my performance index. Oh, this is not that one. We'll just fast forward all the way through this one here. Okay. Okay, so what we're going to do here is, for this very simple problem right here, we could figure out what the here's our function is a tie rod that's in axial, right? And the length is specified. And it must support axial in tension without failing. And what our objective is to minimize the mass of the tie. And the free variables are the cross section and the choice of materials, right? So we have some things available to us as a designer to make choices. So first off, we figure out what the mass is. Well, the mass could be, we could find that if we know the density and we have the area. Right, you'll notice that that's one of our free choices times the length right here, right? So here's the length, where the length is something is specified, area is something that we are free to choose, and rho is something also as part of our material right there, right? We could also say that stress, which is related to strength of the thing, right, is going to be sigma is equal to F over A, right? So what we could say from this is we could write this thing out and say that A was equal to F over stress right there. And we could combine these two things together and say that the mass was going to be equal to density times F over stress times L. And what we'd say, we could rewrite this over here. We say FL is divided by stress divided by rho right here. Now this thing together right here is a performance dependent index right here, right? So we could take something and we have we could call this, if we wanted to, specific strength. And our objective is to minimize the mass of this, right? So we would use this line right here. Let's see. Let's go back to these lines. And do we have one that looks like this right here? Boom. So right here, you see that stress and that density? We would use this line right there. These are the guidelines for the minimum design that we would place onto this right here. Hypothetically now, coming back into our problem here, what if instead we were going to say that we were going to do some amount of the stiffness was also something that we would care about right here. So here's a relationship right here. Here's a stiffness relationship. And that's going to be for a rod FL, displacement is FL over AE. So we can say that A was equal to FL over del E. So if we were to place that back up into here, we could now say that the mass was equal to density FL del E times L. Notably, that right there, F over del is stiffness right there. So there's our stiffness. We could say that what we have here is M is equal to del E K L squared right here. Or maybe stiffness, writing the whole thing out, is M over L squared E del. So right there is a performance index right here. So here's one performance index. Here's another that we might call specific stiffness. And we would use instead this right here, right? So we were taking this line right there, E rho is our specific stiffness that we use as our design guideline. And we would take that and translate it up and down to try to find lines. And you can even see the lines are actually even drawn for us right in here, right? So and sometimes when we're trying to minimize something, it might actually be like below the thing, but because the density is on the bottom right here, I think it's above this line that we would say that needs to be like we need to find the thing. Let me see how much time I've taken up. All right, there's already 16 minutes. I'm not sure we'll be able to cover this in class. To the other example that we might have, just to give you sort of another broad overview, and some semesters this is an entire class worth of material. I decided just to introduce you to it so you had some familiarity with it somewhere in your career. If we want to have light and stiff and it's beam bending now, so you could kind of see a little bit of a comparison to the thing. We know that the length is specified. The beam must support a bending load F without deflecting too much, meaning that the bending stiffness S is specified, right? Or that might be del. I think that maybe this S. I think it would be K. Maybe I would have called it. So the cross section is what we're going to choose, and the choice of material is what our free choices are going to be. So. And it's got a square cross section that really helps us. The area is AB squared. So the mass of the thing is going to be equal to rho AL, and therefore B squared L, right? And the stress of this is MC over I, but we know that the cross section of this is BH cubed over 12, which for us is actually going to be B fourthed over 12, right? Because it's B by B onto the thing. And if we go ahead and do a free body diagram and reactions, here's our F. And we know that the reactions are going to be F over 2 and F over 2. And the shear moment diagram, we get this right here. We would get that maximum moment right there, which is going to be equal to, right, because this is L over 2. So that was going to be actually FL over 4. Right, so it's F over 2 is right here, F over 2 times L over 2, so that's the maximum moment. So we would put this in here and go FL over 4, B over 2, and then B4 over 12. And what we find, we get 2/3 FL B cubed, so that B was equal to 3/2 FL stress to the 1/3. So we could place that back up into here and write out that the mass is density 3/2 FL over pi 2/3 right there, right? So now if we're going to try to figure out what, if the length is something that is set right here, we could bring that back out and say that we have density divided by strength 2/3, and then we'll leave this other part as some other thing that we're going to care about right here. 2/3 right there, right? So the force is probably going to be specified, the length is specified, so all of this is a constant. This is a parameter that's going to vary, right? And it's going to be equal to a particular number. So what we can do is go back up to this right here, and you could see that this is the inverse of that right there, right? This is stress 2/3 over rho, whereas we have rho over 2/3 right here. So we can find a we could find a line that this thing will go back, and we can narrow down and figure out where what family of materials will satisfy and work for us along this lines. So that's like the big idea when it comes to trying to manipulate material selection. As I mentioned, it's a much more involved type of thing. Here's other examples that I've included in the notes here of different material indices in the arrangement. Like, so some of them are already made out for you. So there you go. That's our lesson in material selection, and it was 22 minutes long. I don't know if we'll be able to fit it in class, but I'll be able to post this video, and I don't have any assignments based on this. But this is my first time deciding to try to include it in ME470. So we will maybe revisit this as we go throughout the semester. Thank you.